Hi everyone, so this is your second video and we're going over chemical measurements and solution chemistry. It's the first part of chapter 1. Let's get started. So most of you already know that if you're going to be any type of scientist, you're going to have a good working knowledge of measurements and units and prefixes and converting between units. So the first table that I'm going to show you is table 1.1, which shows your fundamental SI units of measurement, and that would be for the length, mass, time, electric current. These are ones that you should be familiar with already. The table on the bottom shows you SI derived units with special names. So these are ones that maybe you haven't used so often, like frequency, hertz, Newton for the force, pressure, Pascal, but we will be using these in this semester. So I urge you to get to know these units very well because we will be using them for almost every problem that we do. So if you've taken my Chem 231 class, general chemistry class, you know that these prefixes that I'm about to talk about are extremely important, and even more so in this class. You've got your powers of 10, or your orders of magnitude, which you need to know. This is something that is not going to be given to you in the exam. You need to know these like the back of your hand. And it's not the limited list like you had in general chemistry. This is a way more expanded list. As you can see, it goes from iota to yocto. So you better know these. All right, just to practice these unit conversions in powers of 10, let's go ahead and do a problem. In the beginning of this chapter, the box in the front describes the process by which neurotransmitters are released from a nerve cell in discrete bursts. The question says, each neurotransmitter that diffuses to the surface of a nearby electrode releases 2 electrons. Average burst of charge measured at the electrode is 37 femtocoulombs. 1 coulomb of charge corresponds to 6.24 times 10 to the 18th electrons. The question actually asks how many neurotransmitters are released in an average burst. If you remember from my general chemistry class, break everything down and figure out what it is that they're trying to ask you. They want to know how many neurotransmitters are released in an average burst, and if you notice, they give you information of all the stuff that you need. The thing that you start with is there's 37 femtocoulombs, because if you know how many coulombs there's given in an average burst, and you can convert that to neurotransmitters. So what you do is you write 37 femtocoulombs, and you know that 1 femtocoulomb is 10 to the negative 15th coulombs. And if you didn't take my general chemistry course, you know that the power of 10 always goes with the base. So you change the base. So 10 to the negative 15th goes with just the coulomb. And you put a 1 in where the femtocoulomb is. Then you know that 1 coulomb releases 6.24 times 10 to the 18th electrons. The problem told you that. And then the problem also told you that for each neurotransmitter that's diffused to the surface, that releases 2 electrons. So you can put for every 2 electrons, 1 neurotransmitter is released. If you multiply all that out, you get 1.15 times 10 to the 5th neurotransmitters. All right, so this is an easy problem in this class. I need you guys to really buckle down and remember how to do these unit conversions and use dimensional analysis to do these problems. Don't get freaked out by the length of these problems. You got to break them down and take them step by step. All right, let's move on. The next topic we need to talk about is chemical concentration. So as a review, you should remember that the minor species in a solution is called the solute and the major one is called the solvent. In this class and in this text, actually, most of the discussions concern aqueous solutions. So that means that the solvent should be water, unless they tell you. Concentration refers to how much solute is contained in a given volume or mass. And also remember, the amount of stuff that you have in something is Avogadro's number, and I've given it to you here just so you can remember what it is. It's 6.02 times 10 to the 23rd molecules, chairs, desks, acorns, it doesn't matter. It's just 6.02 times 10 to the 23rd stuff equals 1 mole of stuff. So if you don't remember that, I suggest you go back to your general chemistry book and read that over. So you have two major types of concentration units. You have molarity, which is moles of solute over a liter of solution, and then you also have molality, which is moles of solute over kilogram of solution. Molality is not used very often, but I am going to give you the definition of it so you won't get confused if you happen to see it in a problem. So the problem that I want to do to practice your concentration units is here below. It says sulfate, which is SO42-, has a typical concentration of 0.038 molar in seawater. Find the concentration of sulfate in grams per 100 mils. This should be very easy for you. So you set it up as you would set up any other concentration problem. So you start with 0.038 moles of sulfate. That would be moles of sulfate over liters of solution. And then you've got to go to grams of sulfate. So you figure out what the mass of sulfate is, and it happens to be 96.061 grams. So you know that in 1 mole of sulfate, there's 96.061 grams of sulfate. And then you've got to turn it over to milliliters because they want to know in grams per mil, yes, per 100 mil, but you got to go to milliliters. You know that in 1 mil, there's 1 times 10 to the negative 3 liters. So where do you put the power of 10? You put the power of 10 with the base, which is the liters. So 10 to the negative 3 goes on the top, 1 goes on the bottom. So that is the concentration of sulfate in grams per mil. And it happens to be 0.00365 grams per mil, but they want to know grams per 100 mils. So you just go ahead and multiply that times 100, and that would give you the answer. There's 0.37 grams in 100 mils of seawater. We haven't talked about significant figures because there's a whole section, but right now I just want to let you know that there would be 2 sig figs in this answer. All right, let's move on. Other terms that you should be familiar with are electrolytes. We talked about these in general chemistry as well. A strong electrolyte is something that dissociates completely in water, something like magnesium chloride. A weak electrolyte is something that does not dissociate completely. It only partially dissociates. An example of that would be acetic acid. Next thing I want to talk about is other concentration units. So there are other concentration units that we use besides molarity and molality. As a matter of fact, the more common ones are the ones we're going to talk about right now. If I was to go purchase a chemical from a manufacturer, more than likely they're going to come in these type of units. Commercial aqueous reagents like ethanol come as a weight percent. So what that means is the mass of the solute over the mass of solution times 100. They're all times 100 because they're all percents. But the way that you would make this is you would take 95 grams of ethanol and dilute it to 100 grams of solution. Volume percent is just a volume of solute over the volume of solution. So to prepare something like a 5% methanol volume solution, you would need to get 5 milliliters of pure methanol and dilute it to 100 mils of solution. A weight volume percent is just the mass of solute over the volume of solution. So if I wanted to make a 5% weight volume aqueous silver nitrate, I would take 5 grams of silver nitrate and dilute it to 100 mils of solution. These are concentration units that you need to become familiar with because they're the most common ones, and we will be using these throughout the semester. Let's go ahead and do a problem that deals with weight percent. This problem wants you to find the molarity of HCl, hydrochloric acid, in a reagent labeled 37 weight percent HCl, and they give you the density of 1.188 grams per mil. First thing I want to tell you guys is that whenever you see a density, the units that they're given in are usually grams per mil if it's a liquid, and you have to realize that grams is grams of solution. It's not just grams of solute, it's grams of solution. So you start with the 37 weight percent, and we just learned that weight percent is mass of solute over mass of solution. It is a percent, so you can do it either way. I like to go ahead and put 37 grams of HCl over 100 grams of solution. I basically remove the percent from it. You could also do this problem like 0.37 grams of HCl over grams of solution, but I just like to remove the percent. So I have 37 grams of HCl over 100 grams of solution, and then I use the density to eliminate the unit grams of solution. So I say 1.188 grams of solution over 1 mil, and then I want to go ahead and convert the grams to moles of HCl. So I know that there's 36.46 grams of HCl, that's the molar mass, in 1 mole of HCl. I've already got one part of my concentration unit correct. I need moles per liter. So I already got my moles. Now all I got to do is just convert that milliliter that was left on the bottom from the density, convert that to liters. So I know that in 1 mil, there's 10 to the negative 3 liters. So if you notice, all of your units cancel except moles per liter. And that gives you 12.1 moles per liter. All right, let's move on. When we're dealing with concentrations of trace components, we usually express them as parts per million or parts per billion. These are actually the concentration units that I use mostly in my work. So parts per million just means mass of substance divided by the mass of the total sample times 10 to the 6. That makes it into a million, right? So million parts. If I wanted ppbs, it really would be mass of substance times divided by mass of sample times 10 to the 9th. There's several different ways that you can express ppm. A 1 ppm is also equal to 1 microgram per mil or 1 milligram per liter. A 1 ppb is 1 nanogram per mil or 1 microgram per liter. One thing that you should note is that whenever you're doing problems that deal with dilute aqueous solutions, and for whatever reason you think you need the density to finish that problem and they don't give you the density, then you should know that the density of dilute aqueous solutions is very, very close to 1 gram per mil. So that's probably why they didn't give it to you. So don't get confused if you, in a problem, you think, wow, I really need to use density here, but they don't give it to me. If it's a dilute aqueous solution, then it's probably 1 gram per mil. Another thing you should remember is that whenever we're talking about gases, ppm actually refers to volume, not mass, like the original definition that I just showed you up top. So if I had 8 ppms of a certain gas, that really would mean 8 microliters of that gas over a liter of that solution. Just remember that distinction if we're talking about gases. All right, let's go ahead and do a problem that deals with ppbs. So this problem deals with converting between different concentration units. The molarity of C29H60 in winter rainwater is 5.6 nanomolar. They want you to find the concentration in parts per billion, and they give you the molecular weight of C29H60, which happens to be 408.8 grams per mole. All right, so who do you start with? Well, you start with the only thing they give you, which is 5.6 nanomolar. And if it's nanomolar, we know that it's nanomoles per liter. So I put 5.6 nanomoles over liters, and I want to go ahead and convert that liters to milliliters because the concentration that I want to go to is ppb. If you remember, ppb is 1 nanogram per mil or 1 microgram per liter. I'm going to go ahead and change it to nanogram per mil. So I'm going to change that liter to milliliters. So there's 10 to the negative 3 liters in 1 milliliter. Then I go ahead and change the nanomoles to moles. So in 1 nanomole, there's 10 to the negative 9 moles. And then I go ahead and change that moles to grams. In 1 mole of C29H60, there's 408.8 grams of C29H60. And the last thing I have to do is change that grams to nanograms. So in 10 to the negative 9th grams, there's 1 nanogram. If you multiply and divide all that out, you see that you get 2.3 parts per billion, or 2.3 nanograms per milliliter. So the last thing I want to leave you with is a problem. On page 23, you have a section that's called Ask Yourself. I want you to try to do these because these are going to try to incorporate most of the stuff that we've talked about so far. So it says the density of a 70.5 weight percent aqueous perchloric acid is 1.67 grams per mil. So that's the density. And remember what I told you about the density and what the grams actually really means. And they want you to find how many grams of solution are in 1 liter, how many grams of perchloric acid are in 1 liter, and how many moles of perchloric acid are in 1 liter. Like I said, it's on page 23. Go ahead and try these. It would be a good practice for you before your first exam. All right, see you later, guys.